video, I had discussed about discontinuity of Riemann integration function. I had seen a bounded function f is Riemann integrable over the closed interval ab if it has a finite number of points of discontinuity. Also, I had seen a bounded function f is Riemann integrable over the closed and bounded interval ab if it has a infinite number of points of discontinuity. We will see one example. I had seen many examples in my previous video. Just I will review by one example. Here fx equal to 1 over 2 to the power n when x belongs to 1 over 2 to the power n plus 1 to less than equal to 1 over 2 to the power n. When n equal to 0, then by this defined function fx would be 1 when x lies between half less than x less than equal to 1 and when n equal to 1, then this interval would be 1 over 4 less than x less than equal to 1 over 2, and by the defined function for this interval fx would be half and this would be just continue. That means you have understood this type of function has a discontinuity at half, 1/4, 1/8, 1/16, so on. And that means this function has a infinite number of discontinuity, and this set of discontinuity has a limit 0. That means since the function also bounded in this interval, so by this formula f is Riemann integrable on the set close 0, 1. Are you getting? Well, now evaluate the integration 0 to 1 fx dx. To find the integral 0 to 1 fx dx, just write integral 1 to the power 1 over to the power n to 1 fx dx. Then now it breaks at the point in which the function has a discontinuity, and this would be integration 1/2 to 1 fx dx plus integration 1/4 to 1/2 fx dx plus integration 1/8 to 1/4 fx dx up to integration 1 over 2 to the power n plus 1 to 1 over 2 to the power n fx dx. And this is actually equal to, if we put the value here, then this value would be 1/2 to 1 fx dx would be, by the defined function here the value of f would be 1, and by here the value of f would be half, here the value of f would be 1/4, and by the defined function here the value of f would be 1 over 2 to the power n. Then this is equal to, just integrate the equation, this value would be half plus half times 1 over 4 plus 1 over 2 square times 1 over 2 cube up to 1 over 2 to the power n times 1 over 2 to the power n plus 1. If we simplify this equation, then this would be half times 1 plus half square plus half to the power 4 up to half to the power 2n. And notice this is the geometric series, then this value equal to half times 1 minus 1 over 4 to the power n over 1 over 1 minus 1/4, and this is equal to half times 4 over 3 times 1 minus 4 to the power n. And here we have to find the integration 0 to 1. So, if we apply limit here, then this integration would be 0 to 1. Are you getting? And limiting value is equal to, this part would be 0 if we apply the limit. Then this value actually equal to half times 4 over 3. That means this value equal to 2 over 3. That means integration 0 to 1 fx dx would be 2 over 3. Are you getting? How we have to find integration of a function? If the function is Riemann integrable but has infinite discontinuity, here this method is we have to break this integration part, the point in which the function has a discontinuity. Okay? Okay. Now I will see some different type of idea. Now I will see the relation between sequence of function and Riemann integration. I had seen in my earlier video uniform convergence of a sequence of function. I had seen in my earlier video uniform convergence of a sequence of function elaborately. Just recall the definition again. Fn converges to f uniformly on the set A if for epsilon greater than 0 there exists capital N belongs to natural number such that for all x belongs to capital A, absolute value of fnx minus fx less than epsilon, and this is true for all n belongs to natural number. I will see the relation of Riemann integration of function and uniform convergence of a sequence of function. The theorem is, suppose fn converges to f uniformly on the set A and each fn is integrable, then f is also integrable, and limit n tends to infinity, integration a to b fn equal to integration a to b f. Are you getting the idea? That means when sequence of function would be uniformly convergent on the set A, and when each fn is integrable, then n tends to infinity, integration a to b fn always equal to integration a to b a. Okay? To prove the theorem, since the sequence fnx is uniformly convergent, so consider small epsilon n equal to supremum x belongs to closed AB, absolute value of fnx minus fx. And from this expression we can tell easily fx less than equal to fnx plus epsilon n and greater than equal to fnx minus epsilon n. And this expression is true for each x belongs to closed AB. Now, if we apply integral in this relation, then this would be integration a to b fn minus epsilon n dx always would be less than equal to lower integral a bar to b fx dx, which is also less than equal to upper integral a to b bar fx dx, and this is, by this expression, this would be less than equal to integration a to b fn plus epsilon n dx. Okay? And consider this relation as 1. Then, from this expression, we can tell easily modulus of integration a to b bar fx dx minus integration a bar to b fx dx less than 2 times epsilon n times b minus a. And this part is very small part. That means since this part is small, so obviously integral is similar to lower integral. And since upper and lower integral both are same, that may imply f is integrable on the set closed AB. That means I have proved f is integrable. Now, since the sequence of function is uniformly convergent, so obviously this epsilon tends to 0. That means since epsilon n tends to 0, therefore from this relation, since this part is equal, so by this relation we can tell easily just at first see the relation. This relation is equal. So by this relation we can tell easily absolute value of integration a to b fx dx minus integration a to b fn x dx less than epsilon n times b minus a. And since epsilon n tends to 0 as n tends to infinity, so obviously this relation tends to 0. Therefore, since this relation tends to 0, therefore if we apply the definition of limit, then this would be actual integration a to b fx dx equal to limit n tends to infinity integration a to b fn x dx. I will see one example. Fn defined from closed interval 0, 1 to r such that fn x equal to 2nx times 1 minus x square over n. We have to check, is this sequence of function is uniformly convergent on the closed interval 0, 1? At first we have to find the pointwise limit. Limit n tends to infinity 2nx times 1 minus x square over n. This limit is equal to 0 for all x belongs to 0, 1. That means this sequence of function fn x converges to the function fx equal to 0. Integration 0 to 1 f dx equal to 0. Now we have to find limit n tends to infinity integration 0 to 1 fn x dx. This value would be limit n tends to infinity integration 0 to 1 2nx times 1 minus x square to the power n dx. Now consider 1 minus x square equal to u, 1 minus x square to the power n equal to u. Then just calculate oneself. Then this integration would be n over n plus 1 times 1 minus x square. Then the limit would be from 0 to 1. And if we find the value, then this would be limit n tends to infinity n over n plus 1. And this value is, if we apply the limit, then this value is equal to 1. Means limit n tends to infinity 0 to 1 fn dx equal to 1. But 0 to 1 fx dx equal to 0. That means 0 not equal to 1. So, for given function fn x equal to 2nx times 1 minus x square to the power n is not uniformly convergent on the closed interval 0, 1. Are you getting the method? It is always true when the sequence of function be uniformly convergent. But converse of the theorem is not true. The sequence of function pointwise converges to a function f. That does not imply this f is integrable. Okay. Also, the sequence of function pointwise converges to a function who is always integrable, but this relation does not hold always. And actually this relation always will be hold when the function is uniform convergent. Now I will see one example. The sequence of function defined from closed interval 0, 1 to R such that fn x equal to 0 when x equal to 0, fn x equal to n when x belongs to 0 to 1 over n, and 0 when x belongs to 1 over n to closed 1. First notice what is f1. When n equal to 1, then the value of the function is 1, and at the point x equal to 0, the value of the function is 0. That means this would be f1, and f2 would be when x lies between 0 to half, then value of the function is 2, and after that half to 1, the value of the function is 0, and at the point x equal to 0, the value of this function is 0. That means this would be f2, here 1, here 2. Similarly, f3 would be when the points lies between 0 to 1/3, then the value of the function would be 3, and after that the value would be 0, and at the point x equal to 0, the value would be 0, and this process will be continue. Notice one thing, length of the interval getting smaller and smaller when height of the interval become higher and higher. Sequence of function fn x converges to 0 function. That means here fx equal to 0. That means integration 0 to 1 f dx equal to 0. Integration 0 to 1 fn dx would be, here the area of this sequence of function. Here notice this would be the thing. We have to find the integration between the interval 0 to 1 over n. That means this would be 0 to 1 over n, and at this point the value of the fn x is n dx. Otherwise the value of the function is 0. That means this value would be n times 1 over n, which is equal to 1. So, limit n tends to infinity 0 to 1 fn x dx would be 1. Sequence of function be converges pointwise to the function fx, where fx be integrable, but this relation here does not hold. That means this sequence of function does not converges to uniformly. Here converges only pointwise. Are you getting the idea? Defined one question which had come CSIR NET June 2017 exam. The question is fn x equal to 1 over 1 plus n square x square, and this is true for all n belongs to natural number. Then the question, which of the following statement are true? Option 1, fn converges pointwise on the set close 0, 1 to a continuous function. Option 2, fn converges uniformly on the set close 0, 1. Option 3, fn converges uniformly on the set close half to 1. And option 4, integration 0 to 1 fn x dx equal to integration 0 to 1 limit n tends to infinity fn x dx. Okay? At first verify the option fn x equal to 1 over 1 plus n square x square. In the question has indicate we have to find the convergence at the point close 0, 1. Notice fn 0 equal to 1 and limit n tends to infinity fn x equal to 0. That means the sequence of function pointwise converges to 1 when x equal to 0 and otherwise the value is 0. That means this is not continuous. So for this interval the f is not continuous function. That means 1 is a wrong option. Fn converges pointwise on the set close 0 1 to a continuous function. This is wrong option. Option 2 indicate Fn converges uniformly on the set 0 1. Since on the set 0 1 the sequence of function fnx converges to f, which is discontinuous function. So uniform convergent cannot possible. Okay. Option 3 indicate Fn converges uniformly on the set half to 1. The interval half to 1. And in that interval, notice the sequence of function Fn converges to 0 function. That means here fx equal to 0. Okay. Therefore, let's see. Is this sequence of function is uniform in this interval? To find the uniform convergence, I will apply Mn test. All of us know to find the uniform convergence here Mn would be supremum x belongs to half to 1, 1 over 1 plus n square x square. Because here fx equal to 0. And to find the supremum of this function in this interval, consider phi x equal to 1 over 1 plus n square x square. To find the maximum, find the phi prime x. This would be minus 2 n square x over 1 plus n square x square over to the power whole square. And this is true for all x belongs to half to 1. And notice for this interval, this value always strictly less than 0. That means phi x is monotone decreasing function in the interval half to 1. And since this is the monotone decreasing function, so it has a supremum value at the first point, because this is the monotone decreasing, strictly monotone decreasing function, would be 1 over 1 plus n square over 4. Then limit n tends to infinity, mn equal to just 0. Are you getting? That means obviously in this interval, since this function stands to 0, in this interval the sequence of function converges uniformly. Okay? Option 3 is a right option. Fn converges uniformly on the set half to 1. The fourth option indicate limit n tends to infinity integration 0 to 1 fnx dx equal to integration 0 to 1 limit n tends to infinity fnx dx. Take limit n tends to infinity 0 to 1 fnx dx. This would be 1 over 1 plus n squared x square. Now integrate. Consider this nx equal to t. Then dx would be dt over n. Dx has replaced by dt over n and nx square equal to 1 plus t square. And here limit n tends to infinity. Then this value would be, or we all of us know, limit n tends to infinity tan inverse t over n. And this value from 0 to 1. Now put the value. Now after putting the value apply the limit n tends to infinity, this value would be 0. That means this value equal to 0. We have to find integration 0 to 1 limit n tends to infinity fn x dx. The interval 0 to 1 limit n tends to infinity fn x means when x equal to 0 then the value of fn x equal to 1, otherwise the value is 0. That means this integral 0 to 1 limit n tends to infinity fn x dx means this value would be, if we find the integral for this function, this value always would be 0. Therefore, this relation is true. But here interesting thing, in the interval close 0, 1, the function not be converges uniformly. Also, interval close 0, 1, the function converges to f, which is a discontinuous function. That means, so function be uniformly convergent to f, then this relation always will be hold. This relation holds does not mean the sequence is uniformly convergent. And the example is, in this sequence of function, fn does not converges uniformly on the closed interval 0, 1. But this relation has satisfied here. Are you getting the idea? Well, I will stop here. This type of question are very important for any competitive exam. So, I will highly recommend you, please see today's video with pay attention. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel and to share with your friends. Thank you so much.